My name is Ben DeWise, and this is an informational video about the formation and tempering of martensite. I will give a brief introduction to the martensite phase, along with talking about the austenizing, quenching, and tempering processes, as well as going over the properties of martensite. Martensite is a phase formed from its parent austenite phase in the iron-carbon system. Austenite is a phase which exists above the eutectoid isotherm at 727 degrees Celsius. Martensite forms as the temperature of the steel passes over this isotherm. When that happens, the structure changes from a face-centered cubic, which is the structure of the austenite, to a body-centered tetragonal, which is the structure of the martensite. Martensite is a diffusionless transformation. Instead, it involves a shear transformation where there is a sudden shift in atomic structure. This shear transformation causes internal stresses in the structure, which in turn makes martensite into a very hard material. Martensite is not an equilibrium phase, which is why it does not show up in the phase diagram. However, it is not a microconstituent either. It is rather a metastable phase. The post-formation process of steels involves a heat treat process, which is designed to reduce the grain size in the steel and thus increase the strength of them. After the steel is heated all the way through, it is allowed to slow cool, which allows the equilibrium phases to form. This process is known as normalizing. Austenizing is the next step. This process of austenizing is where the steel is heated up above the eutectoid isotherm at 727 degrees Celsius. By heating up the steel, the austenite phase is allowed to form. This is usually done in a range of temperatures from 900 degrees Celsius to 950 degrees Celsius. By heating the steel at temperatures larger than 950 degrees Celsius, the steel can become superheated, which is a problem because when quenching, this can lead to quench cracking because the temperature difference between the steel and the water is so great. Quenching is the most critical step to form martensite, so of course there are some barriers associated with getting a good quench. As I discussed earlier, quench cracking can be a main problem. Like I said, it is caused by plunging a superheated steel into the quench media. Along with this, a higher alloy content also leads to higher cracking potential, as well as the part geometry. What I mean by this is having a combination of thick and thin areas in the steel can result in higher cracking potential. Common quench medias include water, oil, polymer, and salt, with water being the most common because it gives the most aggressive quench. When a steel at high temperature is plunged into the quench media, there is a layer of steam that is formed on the surface. This steam layer is a problem because it does not allow heat to rapidly escape from the part, causing the cooling rate to be less than desired. One way to combat this is to use high-powered jets, which will essentially rip off the steam layer, allowing the heat to escape. You can see examples of this on the two pictures on the right side of the screen. The bottom picture is of an empty quench tank with the jets in full effect. The top picture is of a full quench tank with the jets in full effect. You can see the turbulence of the water created by the high velocity output of these jets. During the first few seconds of the quench is where this rapid transformation occurs at. As I stated before, this martensite transformation is a diffusionless one. Instead, there is a sudden shift in the crystal structure that occurs. The face-centered cubic structure of the austenite rapidly changes to a body-centered tetragonal shape of the martensite. Due to fast cooling, diffusion is extremely restricted. This leaves the carbon atoms with nowhere to go. To make room for them, the lattice must stretch out in one crystal direction. This elongation in turn causes strain on the crystal structure. This strain is what gives martensite its high hardness values. It also accounts for the brittleness of the structure. Martensite forms a needle-like structure. It has a Kürzinal-Sachs relationship to the austenite. This means that the 111 plane of the austenite is parallel to the 110 plane of the martensite. Due to the rapid cooling and shear-like transformation, the martensite plates or needles grow at speeds that approach the speed of sound. When this transformation occurs, not all of the austenite is always formed into martensite. This amount formed depends on the cooling rate. On the top right is what is known as a TTT curve. This stands for time, temperature, transformation. This curve is divided into different sections by the red lines. To form these structures, the cooling curve must pass through the respective areas on this graph. There are two horizontal lines near the bottom, the top one being labeled MS and the bottom one being labeled MF. Ms is the temperature at which the first martensite forms, and Mf is the temperature at which the final martensite forms. It is difficult to get a structure that is 100% martensite, so Mf often refers to the point or the temperature at which 90% of the structure is transformed into martensite. From the curve you can see that the green line passes through the martensite region only. This forms a structure that is completely martensitic. To achieve this, the cooling rate cannot pass through any other sections of that curve. This is where alloying elements really start to help out. Alloying elements will essentially move the nose of this curve back. This allows for a much larger window in terms of what you need the cooling rate to be in order to form only martensite. As stated earlier, it is very difficult to form a steel that is 100% marten. The 10% or less that is left over and not transformed to martensite is referred to as retained austenite. This is not good to have in the microstructure because retained austenite is very ductile. This causes fracture to be much easier. To overcome this issue, the steel is put through a tempering process, which will be discussed later. Martensite in the as-quenched state is a very hard material. This is due to the strains put on from the carbon atoms in the interstitial sites. This strain is what causes the loss of ductility, which leads to the brittleness of the structure. As evidenced from the graph on the top right, the higher carbon content also leads to higher hardnesses. The higher the carbon content, the more and more tetragonal the crystal structure becomes as well. It also leads to a decrease in the martensite start temperature. This makes it more difficult to form as a result of the steel needing to be quenched to a lower and lower temperature. As I stated before, martensite is a hard, brittle structure, oftentimes with retained austenite in it as well. In order to attain better properties, the steel is put through a process known as tempering. This involves heating the steel to a temperature between 175 and 705 degrees Celsius. You don't want to go any higher than this because you want to keep the temperature below the eutectoid isotherm. This is to keep from having austenite grains reform, which would essentially erase everything that was achieved in the quenching process. The toughness of a steel is defined as the area under the curve on the stress-strain diagram. You can see examples of this for 3 different steels on the right. The top diagram shows the toughness of the steels before they were tempered, and the bottom one shows them after they were tempered. The difference in the toughness between the tempered and the untempered steels is very apparent. The time and temperature of the temper is what causes the change in the toughness of these steels. So those are determined by what the desired end product is. Now the tempering process has 3 different stages to it. Stage 1 is where the transition carbides start to form. An example of one of these would be Fe 2.4C. The formation of these carbides start to occur as the steel begins to heat up. As this happens, carbon is allowed to diffuse. As the carbon diffuses out of the martensite and starts to form these carbides, martensite slowly reverts back to its lower energy body-centered cubic form. This transition starts to occur at temperatures around 150 degrees Celsius. Stage 2 in the tempering process is where the retained austenite starts to decompose. The diffusion of carbon is also present in this step and allows the retained austenite to form ferrite and cementite. This solves the problem of the retained austenite that is left over as a result of the quenching process. Stage 2 usually occurs at temperatures from 200 to 300 degrees Celsius. Stage 3 is where the transition carbides formed in stage 1 and the remaining martensite transform into ferrite and cementite. This occurs at temperatures greater than 250 degrees Celsius and is the final stage for low alloy steels. The 4th stage does exist for high alloy steels, however. This is where alloy carbides start to precipitate. This final stage takes the longest because alloys are substitution atoms, so they have a much lower diffusion rate than the interstitial carbon atoms. After the tempering process is complete, you are now left with an extremely tough steel. This concludes my presentation on the formation and tempering of martensite.